Well, hello, ladies and gentlemen. So we're going to continue on powering through the material, begin chapter 4 today, which is in the notes, which is the energy balance or conservation of energy. We'll have seen some of this material before. We looked at the first day of class. We looked at the conservation of mechanical energy equation, and I showed you that it was deficient in the sense that it lacked a few terms: heat, interaction, and the change in internal energy. So we've already looked a little bit at the energy balance, but let's start anew today by declaring the closed system energy balance, E balance, sometimes called the first law of thermodynamics. Energy balance, or the first law of thermodynamics. Let me write down the most basic form of the energy balance. We have the heat minus the work is equal to the change in total energy. And energy is equal to kinetic, potential, and internal. So what that means is the change in internal energy plus the change in potential energy plus the change in kinetic energy. Okay? Now, if we apply this to some system, so here's our system, and it goes from one state to another. So this would be state 2, and this would be state 1. So this is our system. It has a certain amount of mass. It's a closed system energy balance. You don't see any mass being pumped in or being pumped out over the process. So this system with a certain amount of mass is subject to some kind of heat addition, Q1 to 2, and perhaps does some work, W1 to 2, over the process. So this energy balance for this system over the process will look like Q1 to 2 minus W1 to 2 is equal to the change in total energy from state 1 to state 2, which is the change in internal plus the change in potential plus the change in kinetic energy over the process. So that's the closed system energy balance applied to a system that moves between two states, state 1 and state 2. Now let me show you all the various forms of the energy balance. There are many different ways to write the energy balance, just like there are many different ways to write bases of heat transfer and work. Remember we had that table the other day? We had heat per unit mass. We had an infinitesimal process, so we had del Q. We had a rate base, which is del Q over dt. There are many ways to write the energy balance. So basis or bases of E balance. There are a lot of different ways to write the energy balance, and depending on the problem you're working on, one may be more applicable to the problem than the others. So we have bases here. We have expression. And then, of course, we have units. Let's do SI. And, of course, English units. Okay? So let's first write the overall process version of the energy balance. So overall process. For an overall process, closed system, I'm just going to rewrite this equation right here. We have Q minus W is equal to delta E, which is equal to delta U plus delta PE plus delta KE. Okay, so that's the overall process energy balance. The units of all the terms are energy. So in SI units, it would be joules, and in English units, it would be BTU, British thermal units, all right? Now, I can divide this whole equation for the overall process. I can divide it by mass. And everything becomes lowercase or specific quantities. So I can do over all per unit mass. So I just divide every term by mass. And so I get Q minus lowercase w, delta lowercase e is equal to delta lowercase u, delta lowercase pe, delta lowercase ke. All right, so that's per unit mass. That's another way to write the energy balance. It might be useful depending on the problem and what you're trying to find. There's also the infinitesimal or differential process. So differential process. If I take the derivative of this equation, so I get or total derivative, if you like, I get a little bit of heat transfer, del Q, minus a little bit of work, del W. Remember, work and heat are path functions. So you don't write dq and dw here, you write del or delta Q, delta W. And then I have dE. Energy is a point function, so it's dE, not delta E. dE, which is equal to du plus dPe plus dKe. Okay, that's the differential or infinitesimal process. Oh, I forgot putting the units here. Overall process per unit mass. That's going to be energy per unit mass. So we have joule per kilogram, let's say, and we have BTU per slug or pound mass or something, okay? You could say. Differential process, just units of energy. So a joule and a BTU. All right. And then another version you might find interesting and useful, perhaps you'll encounter it, is the rate-based. Rate-based. So how do I get the rate-based? Well, I'm going to take the derivative of the overall process with respect to time. I'll take the derivative with respect to time of every term. And I end up with a Q dot minus W dot is equal to, so the time rate of change of heat, the rate in which heat is added to the system minus the rate in which work is done by the system is equal to the rate of change of total energy of the system. And that's, of course, equal to the rate of change of internal energy plus the rate of change of potential plus the rate of change in kinetic energy. So each one of these terms, for example, so this Q dot is actually del Q over dt. And this E dot, for example, is dE over dt. If you want to know what these terms actually refer to, dot means time derivative. Like in physics, dot means time derivative. So this is the rate based. If you have a problem involving time, probably a good idea to use the rate-based equation. The units for this equation are energy per unit time. You have energy per unit time. So a joule per second or a watt. Watt, which is a joule per second, that's in SI units. And then You could do a BTU per second, but the traditional, for the English system, traditional unit is the horsepower. Could be horsepower, okay? Could be horsepower, all right? So there are 4 different versions of the energy balance, and depending on what kind of a problem you want to solve, either of these may be applicable. Most of the time, you're going to use overall process, most of the time. Some of the times, especially for purposes of deriving equations, and we're going to be doing that soon, you might want to use the differential process. Remember, we talked about specific heat. We define specific heat as the little bit of heat added per unit mass per small temperature change. So specific heat can be defined in terms of a derivative. So sometimes the differential process is the equation to use. And sometimes when you have a problem involving time, it's quicker just to go to the rate-based energy balance. Now, one last thing before we move on and do an example, I want to state that all these versions are equivalent. They all represent the same thing. They're just on a different basis. For example, if I start with the overall per unit mass, I can get to the overall by multiplying the equation by the mass of the system. If I multiply the overall process per unit mass by the mass of the system, all these become uppercase, and I get the overall process equation. How do I get the rate-based? Well, I can take the differential process and divide each term by dt. Change in time, differential change in time, and I get the rate-based equation. Okay? So all of these are versions of the same thing. They're all equivalent. I suggest that you memorize, and most of the time use the overall process. But once you memorize one version, you can always get the others. By taking derivatives, by dividing by mass, multiplying by mass. How do we get, for example, from the differential process to the overall process? Say we started with the differential process energy balance. How do we get to the overall process? You integrate. You integrate over the process. And the del's go away, the d's go away, and you get Q minus W is equal to delta E, et cetera, et cetera. All right? So all these are equivalent. You either take derivatives with respect to something, you multiply by mass, you divide by mass, you integrate. These are all equivalent versions of the energy balance. Okay, let's take a break for a second, and we'll do a couple of examples involving the energy balance for a closed system. Closed system.